Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 4th, 2025. So, just about 2 days ago. This paper tackles alignment drift. That's when a model's safety behaviors get weaker during fine-tuning, and it proposes a framework that can mitigate this drift by up to 50%. The paper is titled AlignGuard-LoRA, Alignment-Preserving Fine-Tuning via Fisher-Guided Decomposition and Riemannian-Geodesic Collision Regularization, and the implications for safer model development are pretty significant. They managed to preserve safety without hurting task performance, and even introduce a new benchmark to measure these effects. Alright, so the core of their framework, which they call AlignGuard-LoRA, is to separate the model's learning process. They achieve this by using a mathematical tool called the Fisher Information Matrix, or FIM. The Fisher Information Matrix basically quantifies how much the model's performance changes when you slightly tweak its internal settings. This allows them to isolate the updates that are critical for safety and treat them differently from the updates needed for the new task, which helps prevent that safety degradation. Okay, so this figure really visualizes that separation across a 30-layer model. We can see the task-specific updates, in blue, are spread throughout, but as we move to the deeper layers of the network, especially layers 25 through 30, there's a heavy concentration of the alignment critical updates in red. This structural split, where different kinds of learning happen in different parts of the model, is a key insight that allows their entire method to work by targeting the right areas. To really measure this alignment drift, the researchers created their own benchmark called Drift Check, and this table shows us some examples. On the left, you have safe prompts, things like asking for a fun fact, or explaining a science concept. But on the right, you have the unsafe prompts, which are designed to really test the model's safety guardrails. These cover everything from illegal activities to hate speech, and they're crucial for quantifying how well the model maintains its alignment after fine-tuning. So, this equation is the heart of how they actually implement that separation. It's essentially a balancing act. On one hand, you have the main task loss, which guides the model to learn its new skill, but then you have these added penalty terms, or regularizers. The Fisher Information Matrix-based regularization penalizes changes to those sensitive alignment directions. And finally, these two overlap terms. Riemannian and Geodesic, they basically ensure that the task updates and alignment updates stay in their own lanes, geometrically speaking, to prevent interference. Alright, and these results really show the impact. On the left, we have refusal accuracy, which is the percentage of unsafe prompts the model correctly rejects. You can see standard methods cause a big drop in performance, but AlignGuard-LoRA stays high, almost matching the original model. Then on the right, we have toxicity probability, where lower is better. Again, standard fine-tuning leads to a spike in toxic outputs. See those red cells? While their method keeps toxicity low, mitigating drift by up to 50%. This table then breaks down exactly why their method works so well compared to the standard approach. While standard low-rank adaptation is global and has no sensitivity awareness, AlignGuard-low-rank adaptation is directional, using that Fisher-weighted penalty. It also adds task stability and controls for update collisions using those Riemannian and Geodesic methods. The result is a shift from weak drift mitigation to strong, targeted protection for the model's alignment. So, to wrap up, AlignGuard-LoRA provides a structured, geometry-aware method to fine-tune models without sacrificing safety. By protecting alignment critical updates, it mitigates drift by up to 50% with minimal trade-offs. That's it for this